Hi everyone, in this video we're going to start talking a little bit about arc length. So we've talked about radians and this ties in really nicely. Arc length is talking about the distance around and outside of the circle. So we talked about laying the radius around the outside of the circle, but we want to be able to figure out, if I know the angle, what is the arc length captured by that angle, the part of the circumference captured. Okay, so we're just using this as an example. If I have point P, and how am I picturing this? I'm labeling this kind of funny. I was imagining that this end is fixed and point P is spinning around. So if it goes through 2 pi radians, I want to know how far does it travel. So 2 pi radians would be all the way around the circle, which means we get the entire circumference. So the circumference equals 2 pi r, and here r is 3 inches. So the 2 pi doesn't have any units attached. This means we're going to end up with 6 pi inches. Okay, next question is what happens if we rotate through pi radians? So I think a really nice way to do this is just to think proportions. And this one's pretty easy to do in your head, but I want to do it a little bit more formally so that we can apply it to things that are less obvious. So if we're looking at pi radians, the way I would do that in my head is say, well, that's halfway around the circle. So we should get half the circumference, which would be 3 pi inches. The way to do that a little more formally is to say pi radians out of 2 pi radians. So this would tell you what fraction of the full rotation you've got should be proportional to I'm trying to decide what to call it. Let's call it S, I think is what I call it later. The arc length divided by 6 pi inches. So the proportion of the full rotation that you get should, the ratio of the full rotation that you get should be equal to the ratio of the circumference that you get. If you've gone halfway around the circle, you should capture half the circumference is basically the argument here. So a nice proportion. You can see the pi's cancel and I get 1/2. If I then multiply, I get S equals half of 6 pi, which is in fact 3 pi inches. Oh, and I didn't follow my units through on that one. No units on the angle side, but the 6 pi is in inches, which means the 3 pi will be as well. You don't have to follow units through everything, but I've been hearing from science folk that people have a hard time doing that, so I'm trying to work that in a little bit more. Okay, so same question for pi over 4 radians, and again, I think that's probably nice enough that we could figure it out on our own. Pi over 4 is 1/8 of the way around, so if we took 1/8 of the circumference, we should get the right answer. But I'm going to again do it the long way because I want to set up something that will work in general, even when it's really not that clear to me what fraction of the circle I have. So if I want to know what fraction of the circle I have, I'm going to take pi over 4 divided by 2 pi. So that should tell me what fraction of the circle I'm working with. And that should be equal to what fraction of the circumference I get. So again, the only units floating around in here are the 6 pi inches, the inches in the circumference. Here, let's call this S1 and we'll call this S2. Okay, so let's see. If we do this, the pi's cancel and we get 1/8, which is exactly what we said before. So basically, if anyone needs to see the fraction work, it's 1/4 divided by 2. You can even leave the pi's in there if you want. Here, we'll do that. Which is the same as multiplying by the reciprocal. So I have pi over 4 multiplied by 1 over 2 pi, and there's the pi's canceling and us getting 1/8. So 1/8 is equal to our second arc length over 6 pi inches, which means our second arc length is equal to 1/8 of 6 pi inches. So we can cancel out a little bit. We can cancel out a 2. So we get 3 pi over 4 inches, or 3/4 pi. That's exactly the same thing, and I hope you'll get really comfortable and good at switching back and forth between 3 pi over 4 and 3/4 pi. Okay, so I'd like to generalize just a little bit. Here, we'll switch colors so you can see. So in general, I would say if I've gone theta radians, if that's my angle, and it really does have to be in radians, just a heads up for later in the quarter when we do degrees won't work in this formula. So if we've gone theta radians out of a full rotation of 2 pi, that should be proportional to our arc length divided by 2 pi r. So I'm being really general here. I'm not talking about the 3-inch radius circle. I'm talking about any circle. So your angle out of 2 pi, which is the whole rotation, should be equal to the arc length that that angle captures divided by the circumference, 2 pi r. And we can solve this for s fairly easily. We would say multiply by 2 pi r, so 2 pi r theta over 2 pi, and the 2 pi's cancel out really nicely. We saw those pi's canceling before, and we get this beautiful little formula right here, s equals r theta. So that's a really nice simple formula. If you just want to remember that, that's great. Otherwise, I hope that what we just walked through shows you how to get it from scratch. If you ever space out, you need to figure out what fraction of a full rotation you've done, and then take that fraction of a full circumference. Okay, so I think I have a couple of examples just to play with this formula. So remember, s equals r theta. And this works only if theta is in radians, because then you have this, how many times does the radius go around the outside thing going on? Okay, so first one, find the arc length of this right here from N to M if the angle here is 1.3 radians. Okay, so these should be pretty straightforward. I just want to make sure you're somewhat familiar with this one. It sneaks up and is really useful in unexpected places. So I try and keep formulas to a minimum. In fact, I've recently cut the area of a sector of a circle. So there's a formula also that gives you the area of this, but I think that we're good with just arc length. If you need that area formula, I'm sure you'll be told about it. Okay, so if we want to use our formula, s equals r theta, S is what we're looking for, arc length. We know our radius is 110, and I didn't give you units, so we'll just stick with that. And we know our angle is 1.3 radians. So I feel like I should do that in my head, but it's late and I'm not going to. If we do 110 times 1.3, we get 143. And again, since we weren't given any units on the radius, we'll just leave that unitless as well. Whatever the units of the radius are, they should carry through to the arc length. So I know I give you some in your homework that are very slightly trickier. I might give you an S and an R and ask you for a theta, or an S and a theta and ask you for an R. But basically, this is a very simple formula, and I just want you to be familiar with it. So it hopefully won't get too crazy. A couple more of these. One of the world's most famous clocks, Big Ben, has a minute hand that is 14 feet long. We would like to figure out how far the tip of the minute hand will travel in 7 minutes. Okay, so we don't have a starting time, but it shouldn't matter. It's all about what sort of angle we capture. So again, this is asking for an arc length. I know because the tip of the minute hand is moving around in a circle, so it's not just straight line distance, it's this arc distance. So for example, if we start on the hour, let's see, 15 minutes, so 7 minutes isn't very big. We would need some idea of what that angle was. And I can actually think of a couple ways to get this. You can do your proportion in terms of radians, or you could just figure out what fraction of an hour 7 minutes is. So it would actually work out for us, I believe, to say 7 over 60 is our fraction of a full rotation. But if we want to figure this out, we can also go back to proportions and say, okay, we want to figure out, what do we want to figure out? We want to figure out if 7 over 60 is proportional to our angle over 2 pi. Then our angle is 14 pi over 60. And I think we can even do a little better. We can cancel out a 2. 7 over 30. Oh, sorry, that's a theta. So 7 pi over 30 is what we're getting. Okay. So over here, S equals R. Our radius is 14 feet. And then we have a 7 pi over 30. Okay, so if we get 14 times 7 pi over 30, what can we do here to simplify? We can cancel out a 2 again. Okay, so 7 times 7, so I'm seeing 49 pi over 15 feet. Okay, so maybe I lied to you. The 7 over 60 we use, but I don't think we could just put that in here nicely. We really do want that radian measure. Okay, one more, and this is a word problem, so if you want to convert that to a decimal, I am fine with that. We're going to work with a lot of pi's and square roots and messy things, and on the first couple of exams, you're not going to be allowed to use calculators, so you do want to practice getting these nice exact answers and not worrying about switching to a decimal. Okay, I think this is my last one. Yeah, it is. A windshield wiper blade is 20 inches long and is attached at its midpoint to a 16-inch long arm. The arm rotates through an angle of 2 radians. So that's the full swipe across the windshield is 2 radians. And we want to first figure out the distance that the farthest point on the tip of the wiper blade travels in one swipe. Okay, so let me show you what I'm picturing because I think this isn't actually quite exactly what a wiper looks like, but it's a slightly simplified version. So if I have a 20-inch wiper blade and right smack in the middle it's attached to a 16-inch long arm. So right now, like, I should have grabbed colors, but I don't know if anything else will show up on here anyways. So this is the point that we're rotating around. It'll head out this way as well. Okay, let's see. So this is 10 inches and this is 16 inches. I don't think we'll need this, but there's this 6-inch gap here that it's not hitting. So the entire length of this thing is, what is it, 26 inches. Okay, so if all that mess makes sense, I hope it does. If we want to figure out how far this tip swings, we don't just want to include the 20 inches, we want to do the entire length, the 26 inches. So we're going to use, we're looking for arc distance, S equals R theta. For R, we're going to use 26 inches. And we were just told that one swipe is 2 radians, so we just have to double that, which means that S is equal to 52 inches. Okay, and then in this second one, if the blade makes 2 swipes per second, how fast is the tip of the blade moving? Okay, well, we know this. In one swipe, it goes 52 inches, which means in 2 swipes, it will go 104 inches, which means that its speed, how fast is the tip? Yeah, so that point on the tip of the wiper blade is going 104 inches per second. That sounds quite fast. I think I might be making up how fast this wiper goes. I don't think they really make 2 swipes per second, but we'll pretend. Okay, I think that's it. Thanks for watching.